Hello everybody. Today I'll present our paper on the expressive equivalence of TPTL in the pointwise and continuous semantics. In our paper, we introduce a first-order logic which can be used for specifying properties of real-time systems, and we'll introduce two natural interpretations of the logic, the pointwise and continuous semantics. We show that this logic is equally expressive in both these semantics, and as a result, from this theorem, we can conclude that the logic TPTL introduced by Allure and Henzinger, when we endow this logic with the since operator, then that logic is also equally expressive in its pointwise and continuous semantics. We interpret our logic over time words. A time word is a sequence of tuples which are of the form an action followed by a timestamp. So this time word has an action A at 0, A at 2, B at 2.5, B at 3.8, and so on. Along with this, our logic has simple constraints. A simple constraint is a constraint of the form x related to y, where x and y are variables, or x related to y plus c, where c is a rational constant, and the relation can be any one of these five. Now we describe the logic. We call our logic a first-order logic with simple constraints, and we interpret it over timed words, which are over a finite alphabet capital sigma. The formulas that we allow in our logic are A of x, an atomic formula which says that an action A has occurred at x. G, which is a simple constraint. We allow the standard Boolean operators, and we allow first-order quantification. Now, this logic can be interpreted in two ways, which we call the pointwise and the continuous semantics. I'll describe with an illustration how one interprets a sentence in the two semantics. So consider this time node, which has a bunch of actions A at different times, such as 0, 1.2, 1.8, 2.8, and so on. Now, look at the formula. So what does AX say? AX says that at time X, the action A must occur. So if we take X to be 1.2, then this time word with X equal to 1.2 satisfies AX. But this will not satisfy AX at 0.5 because there is no action A at 0.5. X less than equal to 2 is interpreted as the standard less than equal to. So anything in this time scale will satisfy X less than equal to 2. Anything after 2 will not satisfy. Now, the difference in the pointwise and continuous semantics comes when we interpret quantified formulas, when we interpret a there exists quantification. In the continuous semantics, when we say there exists x and some formula, we mean that the formula must hold for some arbitrary time point x in our time scale. While in the pointwise semantics, we mean that the formula holds for some time point x which has an associated action. So for this formula, x can be only 0, 1.2, 1.8, 2.8, and so on. We cannot have x, let's say 0.5, because it's not associated with an action. Now observe that this formula is not satisfied by this time word in both the pointwise and the continuous semantics. It is not satisfied in the pointwise semantics because there is no action between 0.5 and 1. So x cannot even take any value between 0.5 and 1. It is not satisfied in the continuous semantics because even though x can take values between 0.5 and 1, none of them satisfy A of x. Finally, as a third example, let us look at this sentence, which says there is an x between 0 and 1 and there is no y. It is not the case that there is a y, which is an action A and is between x plus 1 and x plus 1.2. Now, if we interpret this in the continuous semantics, then x can be any arbitrary time point. So let's say x was 0.5. So for x equal to 0.5, this is satisfied. Furthermore, there is no y between 1.5 and 1.7, which has the action A. Observe that 1.5 to 1.7 is empty. There is no action. So in the pointwise semantics, with x in the continuous semantics, with x equal to 0.5, this time word satisfies this sentence. However, if we were to interpret this in the pointwise semantics, then it means that there is an x which is an action point, which has an associated action with it and is between 0 and 1. If we observe, the only value x can take is 0. However, if we take x to be 0, then this is not satisfied, because with y equal to 1.2, this will be satisfied. So the negation becomes false. Hence, in the pointwise semantics, this time word does not satisfy this sentence. Hence, with this, we get one crucial observation, that the same sentence does not accept the same language of time words under the two semantics. Hence, there is a natural question to ask here. Is it the case that for any sentence, if we interpret it in the continuous semantics, there is an equivalent sentence which, when interpreted in the pointwise semantics, the same language? In other words, are the two interpretations equally expressive in power? This is the question we study. So first we will look at whether, given a sentence in pointwise semantics, can we construct an equivalent sentence in continuous semantics? Now this is an easy translation. Suppose we were given a sentence in the pointwise semantics, P. Then to get an equivalent sentence in the continuous semantics, all we have to do is, for every quantified variable x in phi, we have to force x to be an action point. So if we see a subformula of the form there exists x phi prime, we replace it by there exists x capital A of x, which is basically saying x is an action point. So if sigma was a comma b, then capital A of x would be small ax or small bx. So we basically force x to be an action point. Once we do this, it is easy to see that this sentence in the continuous semantics behaves the same way as this would in the pointwise semantics. As an example, consider this phi, which says there is an x is greater than 5, and there is a y greater than equal to x. Now we are interpreting this in the pointwise semantics. To have an equivalent sentence in the continuous semantics, all we need to add is x is a or b, and y is also a or b, because our actions have only two possibilities, a or b. So it is easy to see that this sentence behaves exactly the same way as this sentence when interpreted in continuous semantics. Now we go to the non-trivial direction. That is, given a sentence interpreted in the continuous semantics, how do we translate it to an equivalent sentence when interpreted in pointwise semantics? For this, we'll first look at how we would do it for some simple examples. So consider this sentence, which says there is an x such that it's an action A, and there is a y which is an action B, and y is between 1 and x. Observe that because both the quantified variables are forced to be actions, this whole sentence behaves the same way in both pointwise and continuous semantics. Similarly for this sentence, where again every quantified variable is forced to be an action point. We call such sentences as actively quantified or active sentence. Hence, for an active sentence, regardless of whether we use pointwise or continuous semantics, it will behave the same way. However, if there were variables which were not forced to be action points, such as x in this sentence, we call such variables as passive variables. Now, if a sentence has passive variables, then it might be the case that it expresses different languages when interpreted in the continuous and pointwise semantics. So, to convert a sentence with passive variables, so suppose we interpret a sentence in passive variables with passive variables in the continuous semantics, then to convert it to an equivalent sentence in the pointwise semantics, what we want to do is we want to remove all the passive variables. If we can remove the passive variables, then we know that the sentence behaves the same way in both pointwise and continuous semantics. So that is our aim. To so given any sentence in the continuous semantics, we want to eliminate all the passive variables from that sentence. How do we do this? So we will again look at this by first working on a few simple examples. Consider this. So which is saying there exists x between 0 and 1 and there is a y which is an a and y is between x plus 1 and x plus 1.2. A simple logical manipulation allows us to swap the there exists y and x. So once we swap that, we get this equivalent sentence. Now, in this equivalent sentence, if we can eliminate x from this subformula, then we get a completely active sentence because y is associated to an action point. Now, the question arises, can we eliminate x from this? Yes, indeed we can. For that, we use the Fourier-Motzkin elimination. Fourier-Motzkin elimination allows us to remove a variable x from a conjunction of linear constraints to get a new conjunction of linear constraints such that this holds. There exists x pi x is equivalent to pi prime. So if we apply it here, then it will give us a set of constraints which is equivalent to this formula and does not contain x. So these are the steps of applying Fourier-Motzkin. So once we apply Fourier-Motzkin, the final constraint we get is y is between 1 and 2.2. It is an easy check to verify that if this holds, then there exists x and these two constraints also holds. So using Fourier-Motzkin, we replace this by the formula y is between 1 and 2.2. Hence, our original formula, which had a passive variable x, is converted to one which has no passive variables. Now, one crucial thing to note here is that we were able to swap the quantifiers because both of them were there exist. Hence, if any sentence in our logic can be brought to a sentence which is a nesting of there exist, so we have a x, there exists x, then a y, then a z, then we could repeatedly apply this process and eliminate all the active variables, all the passive variables, sorry. Hence, we would get an completely active sentence. But it turns out this is not possible, but we can get to a form which is almost like this. And that is what we call our normal form. So the norm, to define the normal form, we first say a formula is said to be in exist normal form if it is of the form there exists x, a of x and pi of x. So a is an action, pi is a conjunction of simple constraints, and nu, where nu again is a formula in exist normal form or negation of a formula in exist normal form. So now we want to state the following theorem, that any FOC sentence can be equivalently expressed as a Boolean combination of sentences in exist normal form. We'll illustrate with an example how one does this. So suppose we had this formula. We want to express it in our normal form, which is a Boolean combination of sentences in exist normal form. So observe that this sentence currently has not of an and, which is not allowed in our exist normal form. So the first thing we'll do is we'll push this not through the and, hence it becomes an or. Now ors are again not allowed in exist normal form, so we'll pull the or out. Once we pull the or out, it looks like this. Now observe that this subtree is in exist normal form, and this subtree is almost in exist normal form except for the not a. In our paper, we show a way to eliminate this not a to get a disjunction of formulas which are in exist normal form. In the interest of time, I will not go through that process here. So now once we have it that any sentence can be converted to a sentence in normal form, then we can only look at sentences in normal form and try to remove passive variables from those sentences. So here are two sentences in normal form. This one has a there exist followed by a there exist. This one has a there exist followed by a not of a there exist. We saw previously how one would convert this into a sentence with only actively quantified variables. That is how one would remove x. Now to remove all the passive variables, first we'll try to remove one passive variable. So consider a formula which has one passive variable x and everything else is actively quantified. We will show inductively how one can eliminate the passive variable x from such formula. So suppose psi was true. This is the simplest formula of this form we can have. In this case, phi is of the form there exists x pi of x. We can again use Fourier-Motzkin elimination here to eliminate x. This is the same example we looked at earlier, and where once we eliminated x, we got y between 1 and 2.2. Now, suppose it is more sophisticated. Now we actually have a psi. Now, if psi begins with a there exists y, then we can just swap the y and the x. So we have y here and x here. And now this sub-formula is a smaller formula with one passive variable. By the inductive hypothesis, we know how to remove x from this sub-formula, and hence we'll get a completely active formula. This is the same example we saw earlier. We swapped the y and the x, and then we eliminated x from here, and we got an actively quantified formula. Now what happens if we have a there exists x followed by a not of a there exists? In this case, we can't simply swap the x and the y, because this swapping will not preserve logical equivalence. So in such a case, what we show is that we can find an interval pi1 such that for all x in this interval pi1, this holds. Hence, this formula, we can rewrite it as this formula. So we add a few additional variables, w1 to wn, which are active variables. So we stipulate that they are active variables, and we say that for all x in the interval pi and pi1, so it is the intersection of pi and pi1, the right hand side holds, that is, this holds. Now why does this help us? This helps us because, this not should have been before the there exists. Now why does this help us? This helps us because, now look at this sub-formula. Here we can rewrite this, we can rewrite the for all as a not of a there exists and then push the not inside to get an equivalent formula of this form, which is a negation of a there exists followed by a there exists. Now here we can swap the there exists and then proceed as we had done previously. As an illustration of this there exists to a for all, consider this formula. There exists x is between 0 and 1, and not the case that there is a y, which is an action, and y is between x plus 1 and x plus 1.2. Now, how do we find an interval, a pi1 for x, such that for all x in pi1, this holds? So observe, this is saying that there is no action A between x plus 1 and x plus 1.2. If we can move x in such a way that x plus 1 does not cross over any action point and x plus 1.2 does not cross over any action point, then we will still have that this interval has no action points in it. For example, consider this time node. Let us say x plus 1 to x plus 1.2 was this interval. Now, as long as my left hand side does not cross over this 1.2 or 1.8, so let's say it moved from here to here, even then the interval will not contain any a's. The interval x plus 1 to x plus 1.2 will not contain any a's in it. Hence, we have identified one interval for our x's such that x plus 1 and x plus 1.2 do not have any action A in it. How did we identify it? We ensured that the left boundary never crosses this action or this action, and similarly for the right boundary. Hence, we can formally capture that with this formula by adding 4 new variables for the left hand and the right hand of these bounds. Hence, we have succeeded in eliminating one passive variable from a sentence. This we state formally as a theorem. Now, once we know how to eliminate one passive variable, how do we eliminate all passive variables from a sentence? So for that, we have the following theorem, that given any sentence in continuous semantics, we can translate it into an equivalent active sentence. That is, we eliminate all the passive variables. To do this, first we convert it into a normal form, then in the normal form, in each sentence in there exists normal form, we successively remove the passive variables one by one. As an illustration, consider this. Suppose this triangle was the formula tree for our formula in exists normal form. Then pick the subtree which is rooted at a passive variable and has no passive variables inside it. Let it be this red triangle. We know how to eliminate one passive variable. To eliminate this passive variable, to get a disjunction of some actively quantified formulas. So these are the yellow triangles. Then pull the disjuncts up. So now we have a finite number of disjuncts. Each of them have one less passive variable compared to the original formula. So now from these we can again remove passive variables, and doing this n times we will have removed all the passive variables from our original sentence. Hence, we have succeeded in converting any sentence into an equivalent active sentence. And we know active sentences behave the same way in pointwise and continuous semantics. Now the final part of our paper uses the previous result to show that the logic TPTL with the since operator is equally expressive in the pointwise and continuous semantics. I'll quickly go through the syntax of TPTL. So TPTL allows an action a simple constraint G. It allows negations. It allows the standard Boolean operators. It allows the temporal operator until, and its counterpart since, which allows one to talk about past events. And it allows the freeze quantifier, which freezes the formula theta at the current time point x. Now we'll consider TPTL with since with the operators, with the modal operators of globally and finally, and their counterparts in the backward direction of time. Here, the until and since operator can be expressed using these operators, hence we'll just stick to these operators. Now, the first thing we show is that any TPTL since sentence can be translated into an equivalent FO sentence and vice versa. I'll illustrate this with an example. Consider this formula. It is possibly true, that is, in some future time point, x, a of x is true and x is less than equal to 5. Now this future is from the starting time point 0. The same thing we can express in our FO logic as there exists an x such that a of x and x is less than equal to 5. It is easy to see that both these sentences express the same language when interpreted in their interpretations. Hence, we have a way of translating any TPTL sentence to an equivalent FO sentence and vice versa. Now, using this equivalence, we can prove the final theorem, which is that the logic TPTL with since in the continuous and pointwise semantics are expressively equivalent. To show this, we first start with a TPTL sentence, move to its FO counterpart. Now we know within FO the continuous and pointwise semantics are equivalent, so we do the translation there, and then we go back to a TPTL sentence. Hence, the logic TPTL with since is also equally expressive in its continuous and pointwise semantics. This brings us to the end of the presentation. I'll quickly summarize what we did. So we started with the FO logic. We saw its pointwise and continuous semantics. We saw a normal form for it. We saw how to translate between the two interpretations. And we saw how this implies that TPTL with since is also equally expressive in its two semantics. Some future work that one can do on this is the translation that we did can blow up to a large number of disjuncts because we are constantly adding disjuncts when we do the translation. So one possible thing we can look at is how to make this translation more efficient. Another thing that we did was we restricted our logic to only simple constraints. So one can ask the same question: can is the logic equally expressive if instead of simple constraints we had Pressburger constraints, which are linear integer inequalities? Thank you for listening to me.